What have we done so far is to look at how the evolution of magnetization happens as a function of time by introducing the block matrix, which also introduces the topic of transverse and longitudinal relaxation. I think we ended up applying it for a case of 90-degree X-phase pulse and how it ends up behaving, where the magnetization flips from the z-axis to the minus y-axis when you apply the 90-degree pulse along the x-phase. I hope you did the similar calculation for 90-degree along y, 90-degree along minus x, and so on. And the main things that we ended up learning is that such a thing causes the longitudinal magnetization to go away from its equilibrium, and such a non-equilibrium state recovers by spin lattice relaxation. Similarly, in such a case, transverse magnetization that gets generated due to phase coherence decays as a function of time. We have also seen simulations of that sort. Basically, the idea is NMR experiment has an RF pulse and the signal that ends up coming, which you end up detecting to understand how the system, to characterize the system. And in this regard, in the last class, I introduced a general equation or a formula for how does the transverse magnetization change as a function of flip angle alpha, as a function of offset, and how does the transverse relaxation end up affecting the entire signal. And this is following the application of an alpha degree pulse along y phase. So therefore, mx comes up with cos of omega t, where omega is the capital omega is the offset. Of course, if you ended up having zero offset, this will go to 1 and you'll have no x component. If you ended up having a significant offset, you will actually have a large y component than x component. Such a kind of definition gives a general framework of how the magnetization would be irrespective of the offset that you're trying to look for. And then we also said, why should we keep offset in mind? So that when you have a molecule for which you pick a certain, where you pick up a certain on resonance frequency, and there are offsets associated with the other protons that exist in the system, such a kind of formalism with an offset makes a lot of sense. So with that being the case, we also said that the magnetization that you end up acquiring is something like m plus or m minus, which we call as a single quantum coherence. The single quantum comes from the fact that you excite spins from the alpha state to beta state and beta state to alpha state, which involves a one quantum jump. With that being the case, we said that therefore the m plus of t signal has a functional form m0 times sine alpha, where alpha is the flip angle, exp I omega t, exp minus r2t. This is called a free induction decay. In the lecture I've given what's free, what's induction, what's decay. So go back, take a look at it. The important aspect of this functional form is that it has two very important components. One is the oscillation component, the other is the relaxation component. The oscillation component has the important information of the frequency you're trying to look for with respect to the carrier position omega RF. And you also have the relaxation, which tends to dictate the line width. With that being the case, you get the signal in the time domain, but you want the information in the frequency domain. You end up taking the time domain signal and do something called a complex Fourier transformation, which helps you go from the time domain signal to a frequency domain signal that has two components, the real part and the imaginary part. The real part, we tend to call it the absorptive part, and the imaginary part, we call it dispersive. And we like the absorptive part because it decays as 1 over frequency square, meaning that as you go far away from the frequency of interest, the signal dies faster. On the other hand, the dispersive part dies as 1 over omega, which means that it's going to die slowly. If this is how the absorptive part dies, the dispersive part dies slower. Therefore, we like to have the absorptive signal. An example of which I ended up showing here. This picture is not correct because the maxima should look somewhere like this, where the full width at half height nicely matches the maxima and minima of the absorptive resonance. And of course, the peak for the absorptive comes at the carrier position, or rather, the offset position of the resonance that you're trying to look for. I hope this has given a necessary information to understand how resolution is good for the absorptive line shape and why we want to acquire it. Now, I wanted to give a little bit of an explanation of how does the time domain signal result in a frequency domain spectrum. As I said, this is the way Fourier transformation works, where you have an integrand, you have the time domain signal, you'll be able to extract the frequency domain spectrum by applying this transformation, which is called the Fourier transformation. With that being the case, I am taking the oscillation part and I'm doing it one at a time. I'm taking the cos part, and I said, if you do a Fourier transformation for cos of omega t, you will actually get the solution of omega delta function of omega minus omega, capital omega minus omega, and capital omega plus omega. I have not written it here because I wanted you guys to understand the signal will appear only at plus and minus omega. This is the Fourier pair of the cos part of the free induction decay. No decay right now because decay means you're going to go lesser and lesser. I'm not included decay so far. I'm just showing the oscillation. So oscillation results in a Dirac delta function at the plus and minus value of the offset. Similarly, the sine function, which starts at a 0, has a similar Dirac delta function. And of course, the sign at the minus capital omega will be inverted. This is a consequence of the fact that you can always write cos of capital omega t as exp of I omega t plus exp of minus I omega t by 2. So therefore, what ends up happening? Cos part will still pick delta functions at plus and minus omega. Sine part will also pick at plus and minus omega, but just that sine omega t will be exp I omega t minus exp minus I omega t. The minus sign starts to come. Due to which, when you do a Fourier transformation of the sine part, you still get signal at plus omega and minus omega. Just there, the phase is opposite due to the negative sign. So therefore, what you are able to realize, if your signal is only at capital omega, if you end up doing a sum of these two, you're able to realize that the minus minus gets cancelled and the plus plus get added up, which is why we want to do a complex Fourier transformation to get the signal at the frequency offset with respect to the carrier and not have a mistake that ends up arising from minus omega. This phenomenon of acquiring both the cos and sine part in NMR is called quadrature detection, which is what helps you achieve frequency discrimination. What does frequency discrimination mean? If you're able to realize the cos and sine part cannot discriminate whether it's plus or minus frequency if you only acquire one of them. The moment you do quadrature detection, you will carefully discriminate the frequency that starts to come. You don't get a signal at minus omega, you only get a signal at plus omega. With that being the case, since we just saw how does the oscillation part end up behaving, which is the e power I omega t part behaves in Fourier transformation, the next aspect was to understand the relaxation component to the entire thing. Where if you have an exponential decay that happens in the time domain, it corresponds to the Fourier transformation as a Lorentzian line shape that comes up. So therefore, the oscillation gives a Dirac delta function and the relaxation gives a Lorentzian line shape, which when you end up multiplying in the time domain, results in convolution in the frequency domain, meaning that if you end up taking this shape and literally multiplying it at each point, therefore you're going to get a peak at the resonance frequency with a certain width. I hope this has given you an idea of how the frequency domain signal, which is called the free induction decay, when Fourier transformed, complex Fourier transformed with the quadrature detection, gives you a signal that you are able to detect. Therefore, overall, what have we done thus far? We have been able to go from the fact that we take a molecule, and the molecule has different moieties, which has slight differences in their recession frequency because of the chemical shift environment, which I'll define today, due to which all of them develop a bulk magnetization. Each one of them have their bulk magnetization in the respective frequencies. And then you apply a RF pulse with which you perturb all of them. When you perturb all of them, you end up getting a signal for each one of them, which varies in their offset. And if you end up getting separate signals for each one of them, NMR adds all of them put together to give you a frequency domain signal. So we have been looking at the molecule ethanol for a very long time now. And what did we say? Each one of them have slightly different precision about V naught that comes up due to its chemical environment. Now I'm going to end up defining it omega for each one of them will be equal to 1 minus sigma of the omega naught. You can write it in different ways. Basically, the B field that is experienced as deviations from the B naught field that is applied. And that comes up due to the fact that there is something called a shielding parameter. What is shielding here? We realized that when we took the NMR spectrum or looked at the NMR spectrum of ethanol, the hydroxyl proton came around 5 ppm, the methylene proton came up around 3 ppm, and the methyl proton came up around 1 ppm. These are all approximate numbers I'm giving. And we rationalize this as chemists by trying to say the proton, if bonded with an electronegative atom, comes downfield. One may ask, why is that happening? That largely happens because you have an electronegative atom that's bonded with a proton, due to which what is going to happen, the sigma bond is going to be distorted because the electronegativity of oxygen is greater than the electronegativity of the proton. Due to which, instead of the sigma bond being equally shared, will get slightly shifted towards the oxygen atom. So due to which what happens, the nuclear spin that's being present is seeing a certain electronic environment around it. Similarly, if I end up taking the same for CH2, unlike there's a single bond that's existing between the OH, here the protons are 2 bonds away from the oxygen and are directly connected to the carbon. Unlike the case where the electron cloud will be more towards oxygen for this hydroxyl proton, in case of the methylene proton, it is not going to be as skewed as it's in the case of OH, but it's still going to be slightly skewed because you have a 2 bond separation that comes for these 2 protons, methylene protons you're trying to look for. So due to which the electronic environment will still not be properly shared. Maybe it's still slightly skewed towards carbon, but not as bad as in the case of the OH. Now let's go to the CH3 part. You slowly start to realize that the oxygen is now 3 bonds away, and slowly the effect that the oxygen causes on the methyl group reduces significantly. And in this case, maybe the electron cloud that is shared between the C and H in the methyl group is rather more symmetric. So slowly you start to appreciate the fact that the electronic environment that's experienced by each of this proton varies depending upon the chemical moieties that it is associated with, which is what is defined as the shielding parameter. Since you know these electrons are diamagnetic in nature, they have their own magnetic field, which results in overall shielding of the main magnetic field that you applied. So basically you have nuclear magnets and you have diamagnets and you have a B naught that is applied, all end up influencing the field that's experienced by the proton, which is shown in this aspect. Interestingly, the nuclear shielding parameter is a 3x3 rank 2 nuclear shielding tensor, which means that it has multiple components associated with it. As you are able to see, the distortion that happens for the electronic environment will happen in 3 dimensions. And therefore, it will be affected in all the 3 axes, which is now defined instead of as a single parameter as a 3x3 matrix. But interestingly enough, since we are looking at solution state NMR, there's an averaging that ends up happening, and we pick up only one average for it, which is nothing but the isotropic shielding parameter, which will end up being the trace divided by 3 for this entire system. Meaning that you will not see the anisotropy as a 3-dimensional parameter. You just see it as a scalar variable, which ends up affecting the local magnetic field experienced by a given spin that you're looking for. So what is going to happen, depending upon the value of sigma going to go positive or negative. Therefore, the B naught field, small value, it's not as big as B naught, but it still exerts an influence on B naught. Therefore, what is going to happen, the effective B field that's experienced by a given spin will depend upon what kind of moieties it is attached. Why is it 3-dimensional parameter? You're able to realize that electron cloud is not a 1-dimensional distribution. It has its own 3 dimensions. Therefore, it is a 3x3 matrix. And what we end up seeing is an isotropic value. In reality, what people end up doing is instead of looking at the 3 by 3 matrix this way, we do something called matrix diagonalization, where the sigma will be diagonalized only to its diagonal elements, where yet again, the isotropic sigma will be sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3 by 3. Since it's a rank 2 tensor, the trace should not change. When you do diagonalization, the trace should not change. The magnitude of the determinant of that matrix should also not change. So irrespective of whether you take the trace of this by 3 or trace of this by 3 should be one and the same. But in general, it's defined as after you diagonalize, you take the sum of the diagonal elements divided by 3 to get the isotropic component. This transformation in NMR is generally called the principal axis system, where you go from one where you have all the elements of the 3 by 3 matrix to only the diagonal elements. But I think I'm not going to refer to it too much. So if you don't learn, it's okay. And the parameter which judges how anisotropic the entire system is will be based on this anisotropic parameter. One thing I forgot to mention here is that the moment you diagonalize, it is ordered in a way where the magnitude of 1, 1 is greater than the magnitude of 2, 2, greater than the magnitude of 3, 3. So basically, the magnitude keeps reducing as we go across the diagonal elements. And we define also something called a chemical shift anisotropy, which tells you how anisotropic the entire electronic environment is. Unfortunately, solution state NMR cannot directly pick it from isotropic experiments. We only end up picking the isotropic shielding parameter, which ends up affecting the frequency at which they process. And therefore, what is going to end up happening, you are able to realize the omega for each of them is going to be quite different, which is why each of them comes at a different, we can't call it omega naught. The Larmor precession frequency of proton is constant, but the Larmor precession frequency of the proton that you're trying to look for depends in addition to its nuclear shielding parameter as well. So each of the omega I could be CH3, omega I could be CH2, omega I could be OH, depending upon where the sigma CH3 versus sigma CH2 versus sigma OH, if they are different. When I mean sigma, I'm talking about the isotropic sigma. And why would they be different? They would be different depending upon the atoms that they are coordinating, and the diamagnetic cloud that ends up bonding these two atoms would influence the field that is experienced by a given proton. So therefore, each of them presses at a slightly different frequency from whatever is being applied. Now, if you might remember, the time domain signal is actually given by m naught sine alpha. Let me actually go to the exp I omega t, exp minus r2t. You are able to realize that this has the oscillation. If I have the oscillation, if I do a Fourier transformation, I'll be able to get the Dirac delta function at capital omega. And this gives the Lorentzian. Therefore, both put together, when you end up doing the Fourier transformation, will give you a convolution of Dirac delta with the Lorentzian line shape to give a signal. So slowly you're able to see that the time domain signal already determines how the spectrum starts to look. As an NMR spectroscopist, we would spend most of our time only looking at FIDs, and we would already know how the spectrum would look. So we'll only discuss FIDs over and over again. If that is clear, you're able to realize that the exponential oscillation part has a frequency offset. Let me write it explicitly. Omega is omega naught minus omega RF. Instead of writing omega naught, from now on, we're going to write omega I, where omega I will be given as will be given as 1 minus sigma times omega naught, where the Larmor precession frequency depends on the nucleus, and the precession frequency for a given spin depends on shielding, and the offset that you're trying to talk about depends on that precession frequency with respect to the RF that you ended up applying. So this way, if you're able to get the capital omega from your FID, you'll be able to get your spectrum. I hope you are able to make the transition from magnetization to FID to an NMR spectrum. Now that you guys have accepted the fact that chemical shift comes different for each one of them, there is yet another parameter that matters a lot, which is called scalar coupling. So what do we mean by this? You have a certain offset with respect to OH, you have a certain offset with, offset with respect to a carrier frequency for each of the proton that you're trying to look for. But in addition, what is going to end up happening is that you have a CH3, CH2, OH. What is happening here is that you have a spin in each one of them, where these are also magnets. As much as this magnet ends up interacting with the main B0 field, which is very strong, the nuclear magnets, however tiny they are, also interact with one another. You can imagine this to be a case where you're playing with two bar magnets and the Earth's magnetic field. You can try to get these two so strong that you can try to align them different from the Earth's magnetic field. You can think about it that way. You have two smaller magnets which also try to like to orient themselves in a certain way on top of orienting itself with respect to the B0. This manifests itself through the sigma bonds that are present. Once again, they are mediated by the electrons that bond them. And therefore, these two spins start to interact with one another, which is called the scalar coupling. And how does it influence it is what we'll try to understand right now. I'll give you an idea of how the spectrum looks, including scalar coupling. Say, once again, plotting intensity as a function of energy. The energy in this case is ppm scale. And I said you're going to get one peak at 1 ppm and another at 3 ppm, another at 5. These are not exact numbers. Please don't take me seriously. I'm just giving some moderate numbers so that you will be able to catch up on what is on resonance and what is off resonance. The ppm scale will also get clear in a moment. Maybe I should have defined it before going here, but now that I've started, let me complete this. Interestingly, the methyl group comes as a triplet. The methylene group should come as a quartet. In many of the cases, the hydroxyl group comes as a singlet, but for some practical purposes, depending upon the solvent you put in, you will actually get a triplet. Okay, so in reality, you will get a combination of what's happening to these two for the CH2. Let's not go here right now because it's slightly complicated. Let's start our life with what's happening for the CH3 and OH. What is happening is that you have three equivalent protons, which also see two other equivalent protons next to them. Therefore, what could potentially happen with respect to the methyl proton, the CH2 protons would either both of them align parallel with respect to each other. Remember, they are not pairing. In no way I'm trying to say these two CH2 protons are pairing. Just trying to say one of the orientation could be both pointing together. Another orientation, one could be pairing one way, the other could be pairing the opposite way. And then the last orientation is that both pointing opposite to one another. Okay, so this is what I'm going to be drawing where they are next to each other. In other words, I can say if A and B both can be in alpha alpha, one can be in alpha beta, the other can be in beta alpha, or it could be in beta beta states. Basically, that's what I'm trying to say. And for most common purposes, the alpha beta and beta alpha states are degenerate, which results in the fact that you have a 1:2:1 triplet that you end up getting. Okay, so similarly for the hydroxyl proton, that also sees the same set of partners. The magnitude of the scalar coupling depends upon the sigma bonds that are formed between them. So although both come as triplets, the strength of their coupling depends upon the sigma bond that ends up connecting them. In both these cases, there's a 3-bond coupling that comes up, and the symbol that's given for scalar coupling is J. So you have 3J. In this case, let's call these protons as 1 and this protons as 2. You got 3J12, and you'll also have 3J23 if you call the hydroxyl protons is 3. The magnitude of these could be varying depending upon the strength of the interactions of the scalar coupling. So therefore, the differences that come up here are dictated by these magnitudes, while you're going to get a magnitude of J12 here, you're going to get the magnitude of J23 here. And I hope now it has been made clear. Why do you get something more complicated here? Because the protons here are saying 3 protons. If you have 3 protons, what are the possible states? You can have alpha, alpha, alpha. You know, alpha, alpha, beta, alpha, beta, alpha, beta, alpha, 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 beta, 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 alpha, beta, 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 alpha, and beta, beta, beta for the CH3 as seen from the CH2. So what does this result in? This result in 4 resonances where you have the ratio 1:3:3:1. Yeah. So due to that, first, depending upon the magnitude, I am assuming here, for whatever reason, J12 is greater than J23. Maybe it's not true in reality. On the other hand, if J23 is greater than J12, then instead of seeing this, you're going to see first the triplet splits because of the OH, and then the quartet splits. I hope people are able to see the difference between these two. Most cases for ethanol, you won't see a splitting with respect to OH, but I just thought it'll be a nice way of making you understand how NMR gives you high resolution information in addition to the chemical shift that's decided by the electronic environment around the given spin. The nearby nuclear spins also interact with one another to give you hyperfine splitting information. Yeah, I hope that is clear. Let me pause again and ask if there are any questions. If yes, please come to the mic and speak up.
Sir, why does it depend on the sigma bonds?
Why does it depend on sigma bonds? So basically, once again, I think we had this discussion after the class. You have the diamagnetic electrons that are being present, and those mediate it. Okay, how do the two nuclear magnets talk with each other is the question here. And they mediate this interaction to the sigma bonds that are being present between them. And as you're able to realize, as you have more and more distance from the sigma bond, the effect starts to weaken itself out. Okay. Yeah, so that's why, and you realize that paired electrons are also diamagnetic. They're magnetic in nature. So it's going to propagate it. It's not going to have a spin associated with it, but nevertheless, it's a magnet, isn't it? Yeah, the moments, they have their own mu in some ways. It's going to end up propagating it. They have their susceptibility in one way, which will end up propagating it. Yeah. So slowly, I hope. Sorry.
In a case where the distance is like 3 or 4 bonds, but the orientation is such that they are closer to each other than like 2 bonds, like let's say because of the structure of the molecule. So then, will the interaction be stronger or weaker?
Very, very good question. I'll share a resource where people have documented values for the proton-proton scalar coupling as a function of distance, conformations, and everything. To make the long story short, it depends on all these parameters, in fact. Okay. In the case where these two protons end up being diastereotopic, let's say there's a chiral center here. If they become diastereotopic, the coupling of the geminal protons will actually be higher in magnitude. So all this starts to give hyperfine splitting information in NMR spectrum. So what I'll do is to pick up that source for you and share it with you, where people have done it extensively for different small molecules to understand how complicated the spectra could come up. But although the complication comes up, you have a lot more information to study your system. It's a long and structured story of it. Make sense? Yeah. Any other questions?
I just want to add here, in fact, you can use scalar coupling information to estimate the dihedral angles, and that is used for structure calculations.
That rating let's say you have HA and HB that is coupling. The 3J HA HB coupling can be related to the dihedral angle subtended by the planes containing HA, CA, CB, plane 1, let's say, CB, CA, CB, HB. This will form plane 2. In chemistry, the angle subtended by these two planes is called a dihedral angle. One can relate the 3JHH in a functional form of these dihedral angle. And if you end up measuring it, you'll be able to get what is the dihedral angle between them. Okay, so these parameters are super sensitive and have a lot of information that go with them. In fact, one can actually figure out, even for a cyclohexane molecule, let's say that you have a HA here, which is anti with respect to OH, or you have HA here, which is syn with respect to this OH, the magnitude of coupling would actually be different based on the other proton with respect to the OH that you have, and one can actually measure the differences that start to come out. Now that we have understood how one can get the chemical shift information from NMR, we are now going to understand how on top of chemical shift, we'll get the hyperfine splitting information. And I'm going to do this for a simple case, which if you follow some textbooks, they will call it the AX spin system. I might end up interchanging some nomenclature. Instead of calling it AS, I could call it AX. Instead of calling it AX, I might call it IS as well. What do I mean by it? You can imagine something of this sort, where A is one of them, X is the other one. Or you can also equivalently imagine I and S or A and X. Depending upon textbooks, old textbooks like AX, new textbooks like IS. So I'm going to end up using this as I go forward. I like IS instead of AX. So now let's try to write in its full glory what will be the Hamiltonian for such a case. And what are we trying to talk about here? The influence comes from chemical shift and scalar coupling. So I'm going to call this CS, I'm going to call this J. And we have been seeing the chemical shift Hamiltonian goes as minus gamma H cross B naught. I'm going to write it as B IZ. So basically it goes as minus H cross omega IZ. And if you set H cross to 1, it goes as omega IZ. And the moment you go from omega with respect to omega RF, which means that if you end up applying a pulse, the chemical shift Hamiltonian goes to, sorry, I think I put a minus sign wrong here. The moment you go from minus gamma B is omega, so you have omega like this. The moment you go to the rotating frame, it ends up being capital omega IZ. This is a functional form of the Hamiltonian. All that I have to do is to ask, what is the scalar coupling Hamiltonian? If we understood this, then this entire H Hamiltonian is going to be HCS plus HJ. We have just understood HCS. Now, what is HJ is the question. The functional form of HJ, scalar coupling Hamiltonian, is given as pi j is 2 I dot s. I is given by ix x cap, iy y cap plus iz z cap, and s is going to be given by sx x cap, sy y cap, and sz z cap. The moment you end up doing this, I cap dot s cap reduces itself to ix sx plus iy sy plus iz sz. Of course, there's a 2 in front of it, which I've left out for the time being. Let's also try to imagine what is that we are trying to understand. When you have 2 spins I and S, I could have an alpha state, B could have an alpha, would have an alpha state. We're talking about spin half systems. S could have its own alpha and beta states. Since it's proton we are trying to talk about, for both the cases, gamma is greater than 0. If these two are isolated spin systems, that means, what do I mean by an isolated spin system? If I and S are isolated, let me try to give an example. You could have a case where you have HA here, you have, say, C, just as an example I'm giving. In most cases, the coupling of the HA to HB is going to be, oh, no, it's not even 3 bonds, it's more than 3 bonds. Talking about 1, 2, 3, 4 bonds, right? The 4-bond coupling will be approximately equal to 0. At that moment, you can treat these two protons as a completely independent system, each of them having its own frequency offset. Therefore, you're only going to get a spectrum with both being singlets. Although they have their own alpha and beta states that are being present, the alpha beta states don't end up coupling, meaning that their magnetic fields don't end up influencing each other. So they come as separate singlets at their respective offsets with respect to the carrier transmitter frequency omega r. But the moment you start end up interacting them, where the magnitude of J is not 0, I'm not committing whether it's 1 bond, 2 bond, or anything. I'm just picking 2 IS spin system. In that case, what is going to happen? You're going to have 4 states that are going to be present. With those 4 states being present, the first question that comes up, what is the difference in the chemical shift between the 2 states with respect to 2 pi j is? In many of the cases, you will have the chemical shift difference much greater than the scalar coupling magnitude. Why do we have a 2 pi here and no 2 pi here? Remember, we want to compare things of similar units. Currently, I'm assuming this is in radian per second. Therefore, in order to make it per radian per second, we are having 2 pi j here. If you want to compare hertz to hertz, you take the 2 pi this side, you get the chemical shift difference in hertz, and you get the j coupling in hertz to understand this thing. And for today's lecture, we are going to associate ourselves only with this case, but there are also other cases where, when the scalar coupling dominates or equals or even dominates greater than 2 pi j is. I'm not going to deal with this today. I'm only going to significantly deal with this. If we have time, we will take a look at this much later on in this course. Luckily, when you have the situation A, this is called the weak coupling approximation. What ends up happening is that I dot S can be approximately equal to only IZ-SZ component. Basically, you're trying to say IX-SX plus IY-SY is approximately equal to 0. This is called the weak coupling approximation. In more rigorous terms, it is also called the secular approximation. I won't have time to go into this for the time being, because I want to ensure that you understand how this chemical shift or scalar coupling comes on top of chemical shift. So under this assumption of weak coupling approximation, immediately what happens? I'm not going to deal with this right now. Under the weak coupling approximation, the scalar coupling reduces itself to phi j to Iz SZ. Okay, so now what we have done is to construct the entire Hamiltonian as a sum of chemical shift and scalar coupling. And therefore, the entire Hamiltonian is going to be for an ith system, or rather, let's write it for spin I. It's going to be omega I. Let's write it for the entire system. I'm sorry. Omega I plus 2 pi j IZ-SZ, assuming weak coupling. Now, of course, here I'm entirely missing out on the S spin. You will also have omega S SZ, which is the precession component of each one of them. Of course, in the example I took earlier where the J coupling is small, the Hamiltonian is only going to be omega IIZ plus omega SSZ, because we said JIS in that case was approximately equal to 0. In this case, the magnitude of J is not being equal to 0, then you have the scalar coupling that comes on top of this entire system. Let me write the Hamiltonian again. Hamiltonian is going to be omega IIZ plus omega SSV plus 2 pi J IZSC. And now I'm going to apply it on the alpha alpha state. What do I mean by the alpha alpha state? The first index corresponds to I, the second index corresponds to S. So what is going to happen? You're going to get omega I by 2 plus omega S by 2 plus 2 pi J IS 1 by 4. Why did we do this? If you operate IZ on alpha, you get half. You get operate SC on alpha, you get half. IZ does not operate on the S component. SC does not operate on the I component. So therefore, you're only going to get half of each. On the other hand, the IZ and SZ that you're trying to put will interrogate their respective spins. So you're going to get half over half. You get 1 over 4. With that being the case, you actually get the energy as sigma I omega I by 2 plus omega S by 2 plus pi J. I'm going to drop the index IS from here on divided by 2. Similarly, if you end up applying this for an alpha beta state, I'm going to go slightly faster so that I can finish the lecture. You're going to get a negative sign for the S part and the J part because S part is in beta. Similarly, you apply for beta alpha state, you're going to get omega minus omega I by 2 plus omega S by 2 minus pi J by 2. And Hamiltonian on beta beta is going to be minus omega I by 2 minus omega S by 2 plus pi J by 2. The plus comes because you have minus half times minus half, that makes it plus half. Okay, with that being the case, what you guys are able to understand, remember there is a negative sign with an omega because it goes with small omega, and small omega goes with minus gamma b naught. Okay, so therefore anything positive in magnitude will have the lowest energy. So what are we learning from this? The alpha alpha state will be the lowest in energy, given by omega I by 2, omega S by 2 plus pi J by 2. Alpha beta will be like this, omega I by 2 minus omega S by 2 minus pi J by 2. And then the beta alpha is going to be the next state, minus omega I by 2 plus omega S by 2 minus pi J by 2. And the beta beta will be the highest energy state, which is going to be minus omega I by 2 minus omega S by 2 plus pi J by 2. With that being the case, if you guys might remember, we had alpha and beta state for a single spin, which allowed single quantum transitions. Here, the single quantum transitions are one where the first spin doesn't change while the second spin changes. So you could have transitions between alpha alpha to alpha beta, where the first spin remains in alpha. Similarly, the first spin can remain in beta with the second spin transitioning between alpha and beta. So these two are transitions where I'm going to write I remains in beta S goes plus minus. Yet again here, I remains in alpha where S goes plus minus. And you would also have similar transitions happening between these two, where I goes plus minus, where S remains alpha. In this case, I goes plus minus, S going to beta. Immediately you're able to realize you're not going to have two single transitions at omega I and omega S. Omega S has two components. Omega I also has two components. Now, how would you determine the energy difference between them? So you can start calculating what is E alpha beta minus E alpha alpha. This is one transition. So when you take a look at this, where you're subtracting, it goes minus, minus, minus. Therefore, these two get cancelled. These two add up. These two add up. So what are you going to get here? Please go back and do this. I'm going a little fast because I want to finish the lecture on time. It's going to be equal to minus omega s minus pi j. And similarly, if you try to calculate E beta alpha minus E beta beta minus E beta alpha. So first I looked at this transition. Now I'm looking at this transition. This is going to be equal to, what is going to happen? Beta beta has a minus and this is a minus. So therefore anything same sign will get cancelled because they're having a negative sign here. So this is going to get cancelled. This is a negative sign. No negative sign will come here. So these two will add up. And similarly, your positive sign, this is a negative and negative will become positive. So these two will end up adding and you're going to get minus omega s plus pi j. And similarly, try to do for E beta alpha minus E alpha alpha. That's going to be minus omega I minus pi j, and E beta beta minus E alpha alpha will be minus omega I plus pi j. Why did we do this? You realize that the energy difference comes up in the E power I omega component, which is the oscillation component. And therefore, the moment you end up solving this, you are able to imagine that the EXP components are going to come up as E power I omega. Let me forget the overall negative sign, omega s plus pi j t. That's going to be one component. EXP I omega s minus pi j is another component. EXP I omega I plus pi j is a component. EXP I omega I minus pi j is another component. How did I write these parts? I just showed you a moment earlier. These are the energy difference that start to come up. Reason why I switched everything with the minus one is, remember, we are trying to talk about a transition. We say it's going to happen in plus omega, but it depends upon how you end up subtracting the energies. We subtracted beta to alpha, but overall, I hope you're able to understand. You entirely multiply with the minus sign. It's going to be plus, 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 minus, plus, plus, and plus, minus. So that's essentially what I've written here. The reason why this is done is that from here, if you end up Fourier transforming, you will therefore end up getting a spectrum where you have signals at omega I and omega s. I'm not even writing minus omega I and minus omega s because we are assuming we will do quadrature detection where you get proper frequency discrimination. So I'm not even telling you where the offset is, and we are doing it in general terms. We do not know the magnitudes of capital omega, right? So therefore, what are you going to get? You're going to get two signals at each one of them separated by 2 pi j. Why is it 2 pi j? You're talking about one where it's omega I plus pi j, another one omega I minus pi j, omega s plus pi j, omega s minus pi j. So therefore, if you take the difference between these two, the 2 pi j will come up as the difference between each one of them. So this is how, for a two spin half systems that interact with one another, you get hyperfine splitting. So if you go back to the syllabus, I just ended up talking to you about the AX system. You can complicate your life by having AX2, AMX, AMX2. I'll give you a quick idea of what do I mean by them. So you could have examples. This is what your practice assignment for this week is going to be. You have a spin system that looks like this, for instance. So this is what we call as the AMX X system. Oh, sorry, yeah, you can go for the AMX system. You can always approximate AMX to X2, or you can also write it any which way that you want. You can call it an A, N, and X system. Okay, where you have JAM, JAX, and JMX that might be present. Okay, and what I want you to do is to set up, there are going to be alpha, beta for these, alpha, beta states for this, alpha, beta states for this. Put them together, determine what are their energy levels the way we just did. Okay, you can assume magnitudes of omega A, omega M, omega X in different ways and solve it for an MAX system. On the other hand, you could also solve it for a AX2 system where you have.
We need to wrap up. Next person is waiting.
Okay, I'm very sorry. A and X where both are equivalent, where you could have an AX2 system. So my request is that go do this as an assignment. I'll try to post the solutions for it. If there are any questions, please raise it in the classroom. Remember, next Wednesday is the quiz, so please make sure you prepare and come. And thank you very much, and sorry for the delay, Jeet.